True. Hello, students. Welcome once again for the GATE lecture, live lecture on strength of materials. Today we are taking the topic of columns, columns and studs. Basically, the name is columns and studs, and we will deal with the long columns only. That is Euler's theory of columns, right? So columns may be divided into three parts basically: short column, medium column, and long columns. Right? Long columns you have seen in your houses where there is a long pole or structure is there. A lot of load is taken by the building load is taken by the columns. Right? So columns may fail in direct stresses and direct compressive stresses because columns are taking the compressive stresses only, right? So basically the compressive stresses are there. So it may fail due to direct stresses if this is a short column. But if the column is a long column, the failure is due to bending, right? So suppose there is a column like this. I'm making a single line, but it is a column. It has some width and a load is applied, so there may be a buckling in the column, right, like this. And due to this buckling, due to this deflection, there may be some failure of the column before the actual stress reached in the column, right? Maybe the direct stress is very high where it may fail if it would have a short column, but because it is a long column, so it fails earlier due to the bending or buckling, right? Why we are saying buckling? Because there is slight difference between bending and buckling. Bending is a fixed fixed deformation like this. Suppose this is a beam and a load is applied here. This is a sort of bending because we know where it will go, it will deform, right? But in buckling we don't know in which direction it will buckle. Mainly it will buckle in the direction where the moment of inertia is minimum, right? So because the direction, the buckling direction depends on something else, like moment of inertia or radius of gyration, minimum radius of gyration. So that's why we are naming it like buckling rather than bending, but it is actually bending. So, so we will first define a term that is called slenderness ratio. Slenderness ratio. What is this slenderness ratio? So it is the ratio of, it is the ratio of length of the column to the minimum radius of gyration. Radius of gyration, because radius of gyration is associated with moment of inertia, and the buckling takes place in the direction where there is low moment of inertia, minimum moment of inertia, that is minimum radius of gyration, right? And because it is minimum radius of gyration, because it is weak in that portion where the buckling takes place, right? So that's why we are taking the minimum radius of gyration, right? And here length, when we say length, length is actually the equivalent length. We can use the word, the better word is equivalent length, equivalent, right? So it means slenderness ratio is equal to equivalent length of the column divided by the minimum radius of gyration. Right? This is the slenderness ratio. And based on the slenderness ratio, so we can divide the columns into three parts, right? Columns can be classified in three divisions. First is the short column, then medium column, and then long column, right? We will mainly deal with this column, long column, in this chapter, right? And for short column, the slenderness ratio should be less than 32. If the slenderness ratio is less than 32, this is called the short column. And if the slenderness ratio is greater than 120, it is called long column. Length is very large, right? But length in terms of slenderness ratio. And if it varies between 32 to 120, 120, we call it as medium column, medium range column. So we have basically three types of columns. The failure of the short column will be due to direct stresses. Direct stresses. The causes of failure is due to direct stresses, because there is no bending. There is no appreciate bending. So failure may take place due to direct stresses, right? For which our formula is mainly load upon area, right? For long column, the failure takes place due to buckling. Failure takes place due to buckling, or you can say bending. Both are same thing. I have told you that there is slight difference between buckling and bending, right? And in this case, medium column, the failure may take place the combined effect of direct stress and bending stress, right? So this is the combined effect of direct stresses and bending stresses. Right. So this is the concept of the columns, right? So we will deal with the long columns and Euler's theory of column. Wait a minute. So let us continue. Let us continue, right? We were talking about the columns. There are some assumptions. There are some assumptions associated with the columns, right? Assumptions for Euler's theory of columns. When we discuss about the Euler's theory, it means we are discussing about the long columns only, right? So we are taking the column into consideration, the long columns, right? So Euler's theory is applicable. Euler's theory is applicable for long columns only. Because for short columns, we have the direct stresses formula is there, so we can directly apply the direct stresses. So it is applicable for long columns, right? And the slenderness ratio greater than nearly equal to 80, right? For if we talk about different materials at different range of slenderness ratio. If we talk about mild steel, so the slenderness ratio should be greater than or equal to 80, right? Because when the slenderness ratio is greater than 80, although it is a medium column, right? But still we can neglect the direct stress failure, and we can assume that the failure takes place due to bending stresses or buckling stresses only, right? So that's why we are taking this is nearly equal to 80, right? Secondly, we say that when we are applying the load, compressive load, we are assuming that there is the weight of the material itself. Weight of the material itself is neglected, right? So whatever load is applied, this is called Euler's load. This PE is called Euler's load, right? So the self weight of this material, the material of itself, is neglected, right? So self weight of material is neglected, right? And we discussed that the failure take place due to buckling only, right? Here we are assuming that failure takes place due to buckling only, right? Effect of direct stresses are very small, right? So this is the some assumptions of the columns, right? And after the deformation, after the buckling, the plane on which the we are applying the load is remains same, right? Plane before and after the application of load, planes before and after the application of load remains, it is not deforming, it remains same plane, same condition, right? So this is some assumptions while deriving the Euler's theory of columns, right? So Euler's theory of columns is the best judge of the, although there are many theories are there, Rankine theory is there, But Euler's theory of column is the best judge for the long columns, right? So for long columns, it is the best part, right? So let us go for the some of the end conditions of the columns, right? Now we are talking about the end conditions, right? So columns, when applied, there are different end conditions of the columns. So we will take few particular type of end conditions on which the failure may take place, right? End conditions of columns. So this is the possibility that the column on which the compressive load is applied, that is a hinge joint at both sides. Most of the long columns are assumed to be hinge joint, right? But the columns which is connected to the concrete structures, that is assumed as a fixed columns, right? So if this is the length of the column and this is pin joint or hinge joint, this is also pin joint, and some load is applied, compressive load is applied. So according to Euler's theory of column, the Euler's load, safe Euler's load, PE is here the safe Euler's load. Euler's load on the column. So for pin joint, this is given by, we are not deriving here, although there is a derivation for that, but we are taking the direct formula here, right? So the failure takes place due to pi square EI upon L square. L is the length of the column, L square, right? Here, what is E? E is the modulus of elasticity. Modulus of elasticity. And what is I? Because we already told that the failure takes place in the direction, buckling takes place in the direction where there is minimum movement of radius of gyration, right? So that's why the moment of inertia should be minimum where the buckling takes place first, right? So this is I is the minimum moment of inertia. Minimum moment of inertia, right? So this is the first condition, end condition, right? Pin joint, right? This is called pin joint. Second we can take the fixed joint, right? Fixed column. So both ends fixed. When the both ends are fixed, right? So let us take, this is a column and both the ends are fixed, right? And the failure take place, buckling take place like this, right? So this is buckling take place due to the application of the load. Load is applied like this, right? So in this case, the Euler's load BE is given by 4 pi square EI upon L square. L is again the length of the column, right? Let us take the third case. In third case, if one end hinged and other end fixed, right? So here, suppose this end is hinged and another end is fixed like this, and load is applied, PE, right? So buckling takes place like this, right? Like this, right? And the safe Euler's load is given by 2 pi square EI upon L square. And let us take the fourth case. This is called one end fixed and other end free. Although there may be many cases, but we are taking these 4 cases. Other end free. So one end is free and other end is fixed like this, right? So the buckling take place like this, right? Like this. Load is applied here, but there is some movement of this free end, right? So this is the course of deformation or buckling, right? So load is applied like this, right? So the safe Euler's load in this case is given by pi square. I am writing directly the formula, although there are derivations for this which is not required for the time being. You can go to theory lectures for the derivations, right? So these are the four main conditions on which the Eulers have given the safe load for uh, to avoid the failure of the columns, long columns, right? We are talking about the long columns, right? As per the assumptions, right? So if you combine all, you can see here there is some symmetry in this Euler's load. Pi square is in every equation, EI is in every equation, L square is also in every equation. There are some constant varying, right, depending on the end conditions, whether it is fixed, whether it is a hinge joint, right? So we can think about taking the reference of the pin joint or the both the joint hinge. We can take the equivalent length. We can define the equivalent length of the columns, right? So what is that equivalent length? So taking the reference, of hinge joint, hinge or pin joint, both and hinge, taking the reference of hinge joint, where the Euler's load is given by Euler's load is given by pi square EI upon L square. So we can find out the equivalent length, right? So in this case, if we take the reference, so this L, the lower term, this can be considered as the equivalent length, right? So if we take the Euler's load in this form, pi square EI upon LE square. So here this LE is called the equivalent length, right? LE is called the equivalent length. So if we take the first case, where both ends were hinged, and where the condition was like this. You have seen here. Both ends are hinged, right? So, and where the Euler's load was given by PE was given by pi square EI upon L square. So in this case, if we compare it, so equivalent length is nothing but the actual length of the column, right? Actual length of the column was L. So actual length of the column, right? If we take second case, where both ends are fixed, like this, the case was like this, and L is the actual length of the column. So Euler's load was given by 4 pi square EI upon L square. L is the actual length of the column. In this case, if we compare equation with equation number 1, suppose this is our equation number 1. If we compare this equation, second equation, with this equation, main equation, so LE can be written as L by 2, half of the length of the column, right? Right. Or third case, one end hinged and other end fixed. In this case, like this, length of the column is L. Euler's load was given by 2 pi square EI upon L square. 2 pi square EI L square. So if we see the equivalent length comparing with the equation number 1, the equivalent length will be given by L by root 2. Root 2, right? And if we take the fourth case number 4, that one end free and other end fixed, one end free and other end fixed, like this, right? Like this. In this case, L is the length of the column. So in this case, Euler's load was given by pi square EI upon 4L square. And the equivalent length, what is the equivalent length in this case then? That is 2L, right? So this chart gives the idea about the equivalent length. So for both ends fixed, the actual length of the column is equal to equivalent length of the column. When both the ends are fixed, the equivalent length is given by half of the actual length, right? So it is quite safe, right? That equivalent length is half of the length is sufficient, which is equal to the hinge joint length, right? So it is very strong. Fixed joint are very strong. And if one end is fixed and other end is hinged, then the equivalent length is given by L by root 2. And if one end is free and other is fixed, the equivalent length is given by 2L. So we will use now this formula. This is our main formula. You have to remember this formula only, right? Pi square EI upon LE square. And equivalent length, you have to remember, this is the equivalent length for each case, right? Right. And slenderness ratio, we have already defined. This is the equivalent length, right? Equivalent length upon minimum radius of gyration, which we have already defined in the previous slide, right? So this is the concept of Euler's theory of columns. So this is some summary background of the Euler's theory of column. Now we can solve some questions asked in GATE or some general questions of the columns, right? So let us solve some questions, numericals on this topic. So now we can solve some questions. Shear force and bending moment diagram we have already discussed. I think some students are asking for shear force and bending moment diagram. We have already discussed. So in any other class we can do the doubt clearing of shear force and bending moment. We have already done in the previous few days back the SFD and BMD. So let us take this question. A column of timber section 15 centimeter by 20 centimeter is 6 meters long and both ends fixed. Both the ends are fixed and the column is 15 centimeter by 20 centimeter. If the Young's modulus for timber is 17.5 kilonewton per millimeter square, we have to determine the crippling load. Here crippling load is Euler's load, basically safe load. When we say crippling load, it means that Euler's load or safe load, right? Which is the this pi square EI upon LE square. So it is pin joint. Both ends are fixed. Fixed joint is there, and Young's modulus is also given, and we have to determine the crippling load and the safe load for the column if factor of safety is given to us, right? So two parts are there. So let us take the first part. In the first part, what we can do is In the first part, we have to find the crippling load, right? So E is given to us. I is I. What is I? So let us draw the picture of this first, like this. This is our column. It is fixed at both ends, like this. Some load is applied on this. That is, we have to find out the safe load or crippling load, and there will be reaction from the bottom, right? So load will be same in static condition, and the dimensions of this is also given. Say this is XX, say this is YY. So dimensions are 50 centimeter by 20 centimeter, right? So suppose this is 15 centimeter and this is 20 centimeter, right? So B is given 15 centimeter, depth is given 20 centimeter. Is it okay? So in this moment of inertia is the minimum moment of inertia. So first we have to find out the minimum moment of inertia, right? Where the buckling takes place, because buckling takes place in that direction, or towards that axis about which the moment of inertia is minimum, right? So I minimum we have to first find out, right? So what is the value of I minimum? Let us solve it. So I minimum, first I xx, we have two axes. So about xx, about yy, we have to find out the moment of inertia. So about xx, I xx, we have to find out. The formula for rectangular section is b d cube by 12. You must be knowing b d cube by 12. So this will be equal to b. B is 15. D is depth, that is 20 cube by 12. So I xx will be equal to 10,000 centimeter to the power 4. 10,000 centimeter to the power 4. You can use calculator and directly values can be obtained. So Iyy is about this axis, about yy axis, right? For yy axis, the cube part will be of b, right? About this axis, right? So the formula will be reversed. That is db cube by 12, right? So this is db cube by 12. So what is d? That is 20. B is 15 cube by 12. So this will be equal to, I am writing directly the result, 5625 centimeter to the power 4. So we have find out Ixx, Iyy, but for this formula, the I minimum is required. I minimum. So what is I minimum out of these two? So you can see Iyy is I minimum, right? So I minimum is basically Iyy. So that is equal to 5625 centimeter to the power 4. This is our moment of inertia, minimum moment of inertia, which will be used in the safe Euler's load equation to find the crippling load or Euler's load, right? So Euler's load now can be find out. PE will be equal to pi square. E is given to us, that is 17.5 kilonewton per millimeter square, right? So we can keep it as millimeter, so that all the millimeters will cancel out and the answer will came in Newton. So we can put millimeter as it is. So we can write 17.5 into 10 power 3 Newton per millimeter square, right? This is the E, the modulus of elasticity. I minimum is centimeter to the power 4. So 5625 into 10 to the power 4 millimeter to the power 4. So this will be 10 into 10 into 10 into 10 to 10 to power 4, right? And now centimeter is converted to millimeter, divided by L equivalent. Now what is L equivalent for fixed joint when both the ends are fixed? So L equivalent will be equal to L by 2, actual length divided by 2. So what is actual length? It should be given 6 meters. So this is 6 by 2 to the whole square, right? For fixed joint, this is L by 2, right? So from here we can find out the Euler's load, and millimeter to the millimeter will cancel out. There is millimeter in here and also in but we have to convert this meter into millimeter also. So this meter should be converted to millimeter. So 6 meters is 6,000 millimeters and divided by 2 square, right? So this is the now millimeter will be cancelled out and the answer will come in meters, newtons, right? So final answer will be, I'm writing the final answer. So final answer will be 1079.5 kilonewton. 1079.5 into 10 power 3 newtons. So Euler's load is basically, the safe load is 1079.5 kilonewton. So this is the safe Euler's load, crippling load for this column, right? In second part, we are given with the factor of safety. So safe working load. So we have to find out the working load, right? So working load will be equal to the theoretical safe load divided by factor of safety. So working load or safe load will be equal to, theoretical load is 1079.5. We have to take the factor of safety into account. So that will come out to be 360, nearly 360 kilonewton. So this is the answer of second part, 360 kilonewton, right? So for first part, we have find out the theoretical safe load based on the Euler's theory. And in second part, keeping the factor of safety into account, we have find out the working load, right? So this is how we can solve the questions of columns, right? Let us take one more example. Check. So let us take the second part. One more question for this. Let us take this question. Yeah, this question. Let us take this question. I will do the screen share, but before that, a 800 millimeter long straight bar of alloy steel and 10 millimeter and 4 millimeter section is mounted on a strut testing machine. There is a strut testing machine. They are testing the strength where the stresses where the it fails, and loaded, actually the load is increased till the bar buckles. The load is gradually increased till this bar buckles. Determine the maximum central deflection before the material attains the yield point of 300 megapascal. This is the stress developed in the material, and we have to find out the deflection, right? We have to find deflection. Let me check the connection. Wait a minute. So in this question we were doing a 800 millimeter long straight bar of alloy steel and 10 millimeter by 4 millimeter section is there. So this type of and this is pin joint, right? Determine the maximum natural load. Assume the Euler's formula for the pin end. Pin end is given to us, right? So this is the case is like this. Case is like this, that this is pin joint. Here it is pin joint. The load is gradually increased. Load gradually increases till the failure take place, right? We have to find that safe load, Euler's load, and length is also given, right? So PE we have to find out. No, we have to find out the deflection. Deflection we have to find out, determine the central deflection. So there is some deflection. This is deformation in the column. We have to find out the central deflection. The deflection at the center will be maximum. So this is delta. So in solution, we have to find out the delta, right? And yield point is given. The safe load is given to us. The stress developed, right? Yield stress is given to us. That is 300 megapascal. E is also given to us. That is 75 gigapascal. What else is given? Dimensions are also given. Dimensions are given to us. That is 10 by 4 millimeter. 10 by 4 millimeter. So depth is say 4 millimeter and width is say 10 millimeter, right? So this is x-axis and this is y-axis, y. It is important because we have to find out the minimum moment of inertia also, right? So delta sigma y E is given, right? We have to find out the deflection and E is given to us, and length is given to us, length that is 800 millimeter, right? So how to proceed? There are two ways to proceed it. First, you can neglect the direct stresses because the failure may take place due to combined stresses, right? So for that you have to find the slenderness ratio. If slenderness ratio is higher, more than 80 or about 100 or 120, you can neglect the direct stresses. Otherwise, you can also take into account the direct stresses. So, if we neglect the direct stress effect, in that case, the failure may take place due to bending stresses only, right? So this is basically the bending stress in that case. This is the bending stress only. And you know the bending formula. What is bending formula? So we can find out through bending formula that m by I equal to sigma by y, right? M by I is equal to sigma y. This is bending stress or yield stress in this case, right? It means that sigma y is equal to sigma b. Yield stress is basically the bending stress if we are neglecting the direct stresses, right? So from here, sigma b can be written as, which is now sigma y, that is equal to my by y. And what is m? This is bending moment. Here m is the bending moment. And what is bending moment? That load multiplied by deflection. So here it is producing a bending moment like this. So here at this point, the bending moment will be given by m is equal to load multiplied by deflection. This deflection we have to find out, right? This deflection we have to find out. So here, this sigma b can be written as m, that is PE into delta into y. Y is the distance, right? That is d by 2 if this is fails due to about x-axis, right? So this is d by 2 upon I minimum, or it is possible that the failure take place due to y axis. In that case, this sigma b will be equal to PE multiplied by delta, this is the bending moment, multiplied by b by 2 divided by I minimum, right? So It depends upon whether about which axis the failure take place, right? So this is I minimum means I axis I y, right? Out of these two, one will be the case, right? So this is basically I x x, and this is I y y. So we have to check first about which direction the moment of inertia is minimum. So out of these two, we have to take that case only, right? So first find out the minimum moment of inertia. So let us find out the minimum moment of inertia. So I'm waiting some. So first find out the minimum moment of inertia, right? So we have written that the sigma b will be equal to my by I pe, delta is the moment, into d by 2 by ixx. Either this is correct, or sigma b equal to pe into delta multiplied by b by 2 if the minimum moment inertia is Iyy, right? These are the two cases. So first we have to find out Ixx. Ixx is bd cube by 12. So this is b is 10, d cube is 4 cube by 12. So this will come out to be, Ixx will come out to be 53.3 millimeter to the power 4. Now find out Iyy, that is db cube by 12. So that will be equal to db cube by 12. So that will come out to be 333.3 millimeter to the power 4. So this is the I minimum. This is basically the I minimum. Right? So we have to choose this formula because the failure take place, the stress developed in this case first, right? So this is the actual formula which to be applied in this case, right? So what is that formula? It means that sigma b, which is the yield stress, which is given by this value, this is equal to pe into delta, this is bending moment, into d by 2 divided by I, which is Ixx, right? So this is the actual formula which we have to use in our equation, right? And what is PE? What is PE? That is pi square EI upon L square, and L is the actual length, right? Because for pin joint, LE and L is equal to, both are equal, right? For pin joint. So now in this case, so we can write here sigma B will be equal to PE, that is pi square EI by L square multiplied by delta multiplied by d by 2 divided by Ixx, because Ixx is the minimum moment of inertia, right? So now just we have to put the values and we can get the answer. So what is sigma B in this case? What is sigma B? Sigma B is, put the values now. Sigma B is 300 megapascal. That will be equal to pi square. Ixx is basically, we have the value is known to us. E is 75 gigapascal. We can convert it to megapascal. So 75 into 10 power 3 megapascal. I, so I to I cancel. This I and this I is both same. So I will be cancelled out, right? So multiplied by delta we have to find out. D is given to us. What is D depth? That is 4 by 2 divided by L square. L length is given to us, that is 800. We are taking everything in millimeter, so that's why the answer will come in millimeter, divided by nothing is to be divided. I is cancelled out because I is both minimum, right? So from here you can find out the deflection of the column, right? Maximum deflection of the column at the center, right? So what will be the deflection of the column? Finally, nearly that is 130 millimeter approximately. So this is the answer of this question. This is the answer of this question. When we neglect the direct stresses, we are assuming that there is no direct stress. Only the failure takes place due to bending stresses. Right? But what if we consider the direct stresses also? If we consider the direct stresses also, so in second case, case 2, considering the direct stresses, then this stress, yield stress sigma y, that will be equal to the direct stress plus bending stresses also, both stresses, right? So yield stress or sigma y will be equal to direct stress plus bending stresses. Because direct stresses are really compressive and bending stresses are compressive on one side and tensile on the other side, right? So these compressive stresses will be add up. So failure will take place the addition of these two stresses. So sigma y will be equal to sigma d, that is Euler's load, which is the safe load applied upon area, plus my by I. This will go to Pe by area. Area is basically B into D. Area is nothing but BD plus, that is PE into delta, which we have to find out deflection. This deflection we have to find out. This is unknown to us, right? So P into delta multiplied by Y, which is D by 2, divided by I, moment of inertia, right, about x-axis. So from here we have to find out the delta, right? And what is PE? P is again that same thing, that is BD pi square EI upon pi square EI upon L square BD plus pi square EI upon L square into delta into D by 2 upon moment of inertia. I to I will cancel out, and finally you will get sigma y will be equal to pi square I upon L square BD plus pi square E delta into D by 2L square, right? This delta we have to find out. Put the values, all the numerical values are available to us. Put the values and you will get the final result of delta. This is given to us, that is 300 megapascal. Put other values also and you will get the value of delta, which is nearly come out to be 129 millimeter. So you can opt the two policies, the considering the direct stresses or neglecting the direct stresses, because failure mainly take place due to bending stresses, right, when we are applying the Euler's formula. So I think we can continue later on these topics, and we have taken a lot of questions on this. I hope that the concept is clear to you. So we can finish the class now, and the next class will be on the next Saturday. On next Saturday there will be class, and at same time we will take another topic. And I hope that you are preparing for your GATE exam, because now it is very close, and GATE exam are very close to you. And best of luck, and you can prepare for your GATE exam. Let us meet on next Saturday at 8 p.m. Thank you.